Okay, let's dive straight in. Have you ever, spent ages getting an AI image just right? That perfect character look.
Oh yeah, definitely.
And then you try to edit it, maybe put the character somewhere else, change the lighting a bit.
And suddenly it's not quite the same character anymore. It drifts.
Exactly, that drift. Or, you just want to make a quick tweak, and the model takes forever to regenerate. Super frustrating.
It really breaks the creative flow.
So what if there was a model that could handle all that? Fast and consistent across lots of edits, and, get this, do both generating and editing in one single system.
Well, that's pretty much the core idea behind the paper we're looking at today. It's called Generative Image Editing in Latent Space. And the model they introduce is FLUX.1 Kontext.
Right, FLUX.1 Kontext. So our mission here is to unpack this paper for you. We want to understand the problem they're tackling, get a handle on the key ideas, how it works basically, and figure out what this means if you're actually building or using these kinds of generative visual tools.
Sounds like a plan.
Okay, so let's do a quick summary up front, kind of the 1-minute version for folks short on time. The big issue FLUX.1 Kontext addresses is how current AI image models often mess up consistency, keeping a character looking the same across multiple edits.
Yeah, that's a huge pain point. Plus, many are just too slow for real interactive work, and you often need different models for making an image versus changing one.
So FLUX.1 Kontext comes in with this new approach. It's a flow matching model, and it manages to combine image generation and editing in just one model.
And the clever bit is how they bring in the context from a reference image. They use this surprisingly simple method of just concatenating sequences of image data.
And the results they're claiming. Big improvements in keeping characters and objects consistent over iterative edits. Noticeably better.
Plus, it's fast. They're talking 3 to 5 seconds for a 124 by 124 image, which is definitely fast enough for interactive use. And the quality holds up against other top systems across different editing tasks.
To back this up, they actually built a new benchmark called KontextBench. It's based on real-world images and tasks. Over 1,000 examples, designed specifically to test this kind of multi-step consistency.
Right, covering things like local edits, character reference, style transfer, and so on.
So the bottom line, FLUX.1 Kontext looks like it could enable much more robust, fast, and consistent creative workflows, fixing some major headaches in generative image editing.
Okay, context setting.
Yeah.
Images are everywhere, right? And the need for editing tools that are powerful but also intuitive and, accurate is just constantly growing.
Absolutely. And generative models, the ones driven by text prompts, have completely changed the game here.
Yeah, compared to traditional editing, Photoshop layers, pixel pushing.
Right, that's direct manipulation. Generative editing is different. It's about the AI understanding your request, often just text, and then synthesizing totally new pixels that fit seamlessly into the existing image.
And the paper breaks down generative capabilities into a couple of main types. First, there's local editing. This is for small, contained changes, like change the car color, but leave the background alone. Think things like in-painting models, llama, stable diffusions in painting. They even mention their own FLUX.1 fill.
Or ControlNet for guiding edits with masks, or Dragon for pushing pixels around geometrically.
Exactly. Then there's the other type, which they call generative editing, or maybe in-context image generation.
This sounds more like taking a concept.
Precisely. You extract a concept, maybe a specific character's face or an artistic style from one image, and then reproduce that concept accurately in totally new images or scenes.
Kind of like how LLMs can learn from examples you give them in the prompt. In-context learning.
Yeah, that's a good analogy. Models like IP Adapter or some retrieval augmented diffusion systems kind of fit here.
And wow, the field's moving fast. We've seen Instruct Pix2Pix, Emu Edit, Omnigen.
Not to mention integrations into big multimodal models like in GPT-4 or Gemini. And platforms like Midjourney, Runway ML are pushing these capabilities out to users all the time.
But the paper argues there are still some persistent problems, even with these newer systems.
Right. To highlight a few key things. One issue is that models trained on synthetic instruction data might inherit some artificiality. They might not produce edits that feel fully realistic or varied because the training data itself was AI generated.
That AI aesthetic they mentioned later, bakiness.
Yeah, potentially related to that. Second, and this is maybe the big one they're hitting, is maintaining appearance consistency across multiple edits.
That drift problem again.
Exactly. If you're trying to tell a visual story, maybe sequence shots for a storyboard, or keep brand assets consistent, this limitation is a major roadblock. Your character just sort of morphs over time.
It's so hard to control.
It really is. And the third point is speed. Some architectures, especially if they're part of larger, say, autoregressive models, can just be sluggish. That kills the interactive vibe.
So enter FLUX.1 Kontext. They're basically saying, we think we've cracked these issues.
That's the claim. A single model for both local and generative editing. And their big focus is nailing that character and object consistency across multiple steps.
While being fast, that 3-5 second generation time for 1K images is pretty compelling.
And it's that combination speed plus consistency that unlocks the potential for truly iterative refinement. You can actually make change after change without the image falling apart visually.
Okay, so how does it actually work? What's under the hood?
Well, the core is a rectified flow transformer. It's related to diffusion models, but instead of learning to predict noise, it learns to predict the direct path or flow from noise straight to the image.
Which can be faster for generating the image.
Often, yeah. It can be more efficient. And like many recent models, it works in the latent space of an image autoencoder, compressing the image first.
And they mentioned training a new autoencoder, a VAE, right? Why bother?
Because the quality of that compressed latent representation is absolutely crucial. If the VAE loses too much detail, the main model can't possibly reconstruct it perfectly, let alone edit it consistently.
Makes sense. Garbage in, garbage out, even if it's compressed garbage.
Kind of, yeah. So they scaled up the compute for training their VAE, used more latent channel 16, they said, and the results in Table 1 show it gives better reconstruction quality, less distortion, better similarity metrics compared to the VAEs used in Stable Diffusion 3 or XL.
So a better foundation. Now, how does the main transformer model handle both the text prompt and the image context for editing?
Uses a kind of hybrid architecture. Some parts process both text and image streams, maybe using cross-attention. Then later blocks focus purely on refining the image tokens after the text information has been sort of absorbed.
And they mentioned technical efficiencies.
Yeah, standard stuff for big models. Fusing operations to reduce parameters and make better use of the GPU hardware using fast attention mechanisms like Flash Attention 3, regional compilation, all aimed at maximizing throughput and speed.
Okay, but the really novel part seems to be how it unifies generation and editing. How does it know whether to make a new image or change an existing one?
This is where that simple sequence concatenation comes in. It's surprisingly elegant. The model is designed to predict a target image, let's call it X, based on a text prompt C. But it can also take an optional context image, Y.
Okay.
If you don't give it Y, it just does text-to-image generation like normal, BXC.
Right.
But if you do provide Y, it performs image-driven editing, PXYC. And the way it incorporates Y is just by encoding it into latent tokens with the VAE, and then sticking those tokens onto the end of the sequence of tokens representing the target X.
Wait, just appending them like text?
Pretty much.
Yeah.
They feed this combined sequence into the transformer. They said this simple approach works well, handles different resolutions, and could even potentially handle multiple context images, though they mainly trained with one.
That feels almost too simple to work reliably. They tried other ways.
Yeah, they mentioned trying channel-wise concatenation, but found this sequential method performed better. Sometimes the simple tricks are the best.
But how does the model differentiate? How does it know these tokens are my reference and these tokens are what I need to generate, especially spatially?
That's the clever bit with the positional embeddings. They use 3D ROPE embeddings, rotary position embeddings, which encode the height and width location of each token.
Okay.
The key trick is they give all the tokens from the context image a special constant offset in their positional encoding. It's like adding a virtual time step or tag that basically says, I belong to the input context.
While the target tokens get a different offset or tag.
Exactly. This lets the model know which tokens are reference material and which ones are part of the image it's currently constructing, while still preserving the internal spatial relationships within both the context and target images.
Got it. It's like invisible labels telling the model the role of each piece of information. And how is it trained?
The main training uses a rectified flow matching loss. They start with a pre-trained FLUX.1 text-to-image model, so it already knows how to generate images from text, and then they fine-tune it.
Fine-tune it on what kind of data?
On pairs, showing the relationship they wanted to learn. So examples of, here's a context image Y, here's a text prompt C, and here's the desired target image icon X. It learns to generate X given Y and C.
Okay, and the speed. How do they get from potentially hundreds of sampling steps down to just a few?
They use a technique called adversarial diffusion distillation, or LADD. Distillation is basically training a faster student model to mimic a slower, more powerful teacher model. LADD uses an adversarial loss during this process.
What does the adversarial part help with?
It helps the distilled model generate higher quality images faster. It can push the model to produce sharper results and potentially avoid some artifacts, like the oversaturation you sometimes get with strong classifier-free guidance and standard diffusion. Their faster Pro version uses this LADD.
And they mentioned a dev version using something else.
Yeah, a guidance distillation approach, likely another method to bake the guidance signal into the model for faster sampling, without needing explicit guidance calculations at inference time.
They also touched on implementation details for large-scale training and safety.
Right, standard practices for training these huge models efficiently across many GPUs. Things like fully sharded data parallelism, FSDP, using mixed precision arithmetic, checkpointing activation selectively to save memory, and importantly, they also mentioned safety training.
How does that work?
They use things like classifier-based filtering to catch potentially harmful outputs, and also adversarial training techniques, specifically designed to make the model less likely to generate certain types of not safe for work or problematic content. Standard responsible AI practices.
All right, let's shift to evaluation, because a big part of the paper is arguing that we need better ways to measure how well these editing models actually work.
Absolutely. They make a strong case that existing benchmarks often fall short. Maybe they rely too much on synthetic data that doesn't reflect real-world messiness.
Or they don't cover the right range of tasks, are low-res, or just aren't available for others to use.
All of which makes it hard to compare models fairly and see if they're truly useful for creative tasks.
So their answer is KontextBench.
Yep, their own benchmark, crowdsourced using real images, personal photos, licensed artwork, and prompts reflecting actual use cases.
How big is it?
It's got 126 unique image prompt pairs, based on 108 diverse starting images. And critically, it covers 5 distinct task categories.
Which are?
Local instruction editing, small changes based on text. Global instruction editing, bigger scene changes. Text editing, like changing words on a sign. Style reference, applying a style.
Yeah.
And character reference, keeping a character consistent.
That sounds much more comprehensive, especially for testing their core claims about consistency.
Exactly. It provides a solid base for human evaluation, which is still the gold standard for judging image quality and instruction following, and they plan to release it, which is great for the research community.
So how did FLUX.1 Kontext actually perform? Let's start with standard text-to-image generation. They had this interesting metric, bakiness.
Yeah, bakiness. It's their term for that overly smooth, maybe slightly artificial, often centrally composed AI aesthetic you sometimes see.
To avoid just optimizing for that, they broke down the evaluation.
Right, Figure 8 shows this. They looked at prompt following, general aesthetic appeal, realism, how well it handles text, typography, and speed all separately.
And the verdict on FLUX.1 Kontext for T2I?
Pretty balanced. It might not absolutely top the charts on, say, pure aesthetics according to raters who prefer that baked look, but it's very competitive across all dimensions. It does well on prompt following, realism, and text. And you see clear improvements going from their Pro version to the larger Max version.
But the real test, given the paper's focus, is the image-to-image editing on KontextBench. Figure 9 has the human evil results. What stands out?
FLUX.1 Kontext, especially the Max and Pro versions, really shines here. They lead the pack in local editing and text editing. And crucially, they're also top-rated for general character reference tasks.
They backed that character consistency claim up with numbers too, right?
Yes, using Auraface similarity scores. Figure 9 shows quantitatively that FLUX.1 Kontext preserves facial identity better across edits compared to the other models they tested against. This really supports their main claim.
Where did it not come out on top?
It was slightly behind the very best models, specifically for global scene editing and for style reference, but still highly competitive overall.
And the speed. Did the benchmark confirm the 3-5-second claim?
Yep. Figure 7b shows the latency. FLUX.1 Kontext models were among the fastest tested, hitting that 3-5-second mark for 124 by 124 images for both text-to-image and image-to-image tasks.
That speed plus the consistency really changes the game for workflows.
Absolutely.
Yeah.
And you see it vividly in the examples they provide. Figure 1 is a great showcase. The same bird character, looking consistent, placed in different scenes, even showed from different angles or duplicated.
And Figure 2, that iterative editing example on the person is really compelling.
It really is. They take a photo, remove an object, then change the location to a beach, then make it rain, and through all those steps, the person's face, their pose, their clothes, they stay remarkably consistent.
That's the dream, isn't it? For anyone doing sequential art or storyboarding.
Totally. And Figure 11 drives this point home by comparing the character drift over multiple turns against other models like GPT-4's image generation and Runway's Gen 2 using those Auraface scores. FLUX.1 Kontext clearly shows less drift, slower degradation.
Which, as you said, is critical for narrative work, branding, anytime you need that visual continuity.
Yeah, and they show more examples, Figure 13 on iteratively editing product shots, Figure 14 on changing facial expressions consistently.
They also show off style reference in Figure 5.
Right, taking the artistic feel, colors, textures moved from a reference image and applying it to completely different subjects. Midjourney popularized this, and other methods like IP adapters can do it, but FLUX.1 handles it within its unified framework.
Figure 6 had that neat product photography workflow. Isolate a subject, put it on a clean background, even zoom in for detail edits.
And Figure 12 shows it using visual cues, like drawing a box to tell the model where to put something, or editing text on signs while keeping the sign's style and the background intact. Very practical stuff.
Now, they are refreshingly upfront about limitations, too. It's not perfect.
No, and it's good they acknowledge that. They mentioned that if you push too far with lots of successive edits, you can still eventually see artifacts creep in or the quality degrade. Figure 10 shows an example of this failure mode.
So not quite infinite editing yet?
Not quite infinite, no. They also note occasional failures in following instructions precisely. Limitations in world knowledge, the model might not understand certain real-world contexts perfectly.
And the distillation process for speed can sometimes introduce small artifacts.
Yeah, a common trade-off with distillation, you gain speed, but sometimes lose a tiny bit of fidelity compared to the original, slower model.
Looking ahead, what directions are they planning to explore?
They list several interesting avenues. Extending the context mechanism to handle multiple input images at once, which could be powerful for more complex edits or blends.
Makes sense.
Further scaling up the model size, which often leads to better capabilities. Pushing inference latency even lower, maybe towards true real-time interaction.
That would be amazing.
And a big one, extending these kinds of robust, consistent editing capabilities into the video domain. Imagine editing video characters this consistently.
Wow, yeah.
But perhaps the most fundamental goal they mention is further reducing that quality degradation during multi-turn editing, getting closer to that idea of infinitely fluid content creation.
Okay, so let's wrap up this AI paper podcast deep dive. We've explored FLUX.1 Kontext, a really interesting model that tackles unifying image generation and editing.
Yeah, its big contributions seem to be that unified approach, the impressive speed, and critically, a major step forward in maintaining character and object consistency across multiple iterative edits.
And validated with their new KontextBench benchmark, which seems like a valuable contribution in itself for evaluating these kinds of real-world editing tasks.
So what does this mean for you listening? Well, if you're an AI researcher, this paper offers insights into flow matching, sequence concatenation for multimodal tasks, and a new benchmark to test against.
If you're an ML engineer, think about the performance potential. That speed and consistency could unlock new kinds of interactive, creative applications.
And if you're anyone using these generative tools, this points towards a future where maybe, just maybe, your characters will actually stay looking like themselves, edits will be faster, and the whole process will feel smoother, more intuitive, less like a constant battle.
It definitely leaves you thinking, right? If we can get to a place where visual identity characters, styles, stays truly consistent across potentially endless edits happening almost instantly, what new kinds of creativity does that unleash?
Exactly. What new forms of storytelling, or rapid prototyping, or maybe even entirely new creative fields could pop up? When the tool can generate completely new realities consistently, on demand, what does editing even mean anymore?